Hi everyone, today in this video I'm going to talk about chapter 12.2 vectors. I'm going to start by the definition and concept with letters, and then I'm going to get into vectors with numbers, applications with numbers. So the definition: a vector is used to indicate a quantity that has both magnitude and direction. It's often represented by an arrow or a directed line segment. So going back to what we know in 2 dimensions, the displacement from a point A to a point B is a vector. We're going to call it V. It has the initial point A and the terminal point where it ends, called B. The direction of this vector is given by AB, and the magnitude is the line segment from A to B. Combining vectors. Let's say we have the vector U and then the vector V. The addition of U plus V is going to be, we're going to start from here where U starts. It goes towards the end of vector V. So in this case, this is going to be U plus V. Remember, U and V are both of them vectors. Same with the subtraction. If we have vector U, for example, and then vector V right here, U minus V, we're going to go from the start of U, and since it's minus V, it's the opposite of V. The direction is the same magnitude but in the opposite direction. So we start here up to this point, and then minus V is going to go down here. So this, from the start towards the end, it's going to be U minus V. Scalar multiplication. If C is a constant and V is a vector, then CV is the vector whose length is the magnitude of C, which is the constant positive number, times the vector V. So times each component of the vector. It's gonna have the same direction as the vector B if C is positive, and it's gonna have the opposite direction of B if C is negative. So what we were doing before, if V is negative, it's going to be opposite, right? If either the constant C of the vector equals 0, then the multiplication between both two is going to be 0, of course. Here we're gonna we have the vector V. We're gonna sketch 2 times V is gonna be same vector V but twice. So this is 1 up to here, and then twice vector. This is gonna be 2V up to this point. Let's say we want 1/2 B. It's gonna be V but half of it, right? So it's gonna be something like this. This is 1/2 V. Then let's say we want negative V, for example. Remember, is multiplied by a constant which is negative. It's -1, so it's going to be the opposite direction of B, but the same magnitude, because we still have the magnitude is V of B is still the same vector. So same vector but in the opposite direction, which is going to be something like that. And then and so on with any other constant. So we have an example here. Let's say we have the vector A, components 4, 3, and 1 on the x and y and z direction, and c equals 3. What's the multiplication AC? So AC is going to be the constant 3 times the vector itself, which is going to be 4, 3, 1. Remember, it's multiplying each component of the vector. So this is going to be vector 4 times 3 on the x direction, then 3 times 3 on the y direction, and then 1 times 3 on the z direction. At the end, we're going to have that AC is 12, 9, and 3. Let's talk about the components. So what we know, it's in 2 dimensions. This is 2 dimensions, and this is 3 dimensions. In 2 dimensions, we have a vector from the origin to a certain point, which is, in this case, we're going to note it as AX and AY. Say vector V has a component on the x direction up to here, and then on the y component, which goes up to here, right? So in this case, V is going to be AX, AY, component AX to the point AX, and AY to the point AY. Sorry, to the variable. Same as in 2 dimensions, but now in 3 dimensions we have 3 variables. Let's say we have a point AX, AY, AZ. We added another variable here. The vector from the origin to the point is going to be, let's say we're going to call it U, is going to have now 3 components as well. So on the x direction is going to be AX, y direction AY, and then AC on the z direction. Remember, this is only from the origin to a point in space 3D. Position vector. It is a representation OP from the origin to the point. So if we go back to what we were saying here, V and U, they are both position vectors, since they both go from the origin to a point in 2D, and this one goes from the origin to a point in 3D. Both are position vectors of the point, of this point, and from this point. Just a straightforward example, we're going to have A equals x1, y1, and c1, and B x2, y2, and c2. Then the vector from A to V in 3 dimensions, of course, because we have 3 variables right here, we're gonna call it A equals components in X. You subtract them, so it's gonna be where it ends, which it ends in V here. So we're gonna have the component X minus the initial component of A. So it's gonna be x2 minus x1. Then on the y axis, it's going to be y2, same final, minus the initial one. And then on the z axis, it's going to be c minus c1. This is going to be vector A from A to B, 3 dimensions. Magnitude or length. Remember the magnitude? It's the line segment, and we're gonna to do that. So let's say we have vector A equals AX, AY on 2 dimensions, and 3 dimensions we're gonna say it's AX, AY, AZ. So the magnitude of A is going to be the square root of each component of the vector squared. So it's going to be ax squared, and you sum them, of course. You add them up and you take the square root of that. So in this case, it's going to be ax squared plus ay squared, square root. Then in 3 dimensions, it's exactly the same, but we add a variable, so magnitude of a is going to be the square root of a component of a and on the x-axis squared plus ay squared plus az squared. We have an example here. If the we have the vector a 4, 0, 3 and the vector v -2, 1, 5, find the magnitude of a plus v. So first, a plus v, remember we add up the components. In this case, it's going to be 4 minus 2, 0 plus 1, 3 plus 5, which is going to be end up being 2, 1, 8. Now, taking the absolute value of a plus b, I'm going to have, remember, the square root of each component squared. So it's going to be 2 squared plus 1 squared plus 8 squared. At the end, we're going to have square root of 4. 4 plus 1, 5 plus 64 is 69. Square root 4 plus 1, 5. Yeah, that's going to be, this is the magnitude of the vector from a to b. Sorry, the addition of a plus b. This is the magnitude. Properties. Doesn't matter what properties of vectors. Doesn't matter which one you take first. If you add them up, the result is going to be the same. A plus b equals b plus a. Then same here, if you add another vector, a plus v plus c plus b plus c is going to be the same as a plus b plus c, because of course we already talked about here, so it doesn't matter how you plug them in, it's going to give you the same result. Any vector plus 0 is the same vector. You add nothing. Here, if you add the vector plus its opposite, it's going to be 0. Any constant, any scalar, times the sum of two vectors is the scalar times the first vector plus the scalar of the second vector. If two constants are added up times the vector, same as that vector times the first constant plus that same vector times the other constant. I don't remember how to call it, but it has a name, the distribution. Two constants multiplied together times the vector is the same. You can take it out, doesn't matter how you multiply them. You can take one constant out and still multiply the other constant with the vector. It's going to give you the same result. And then 1 times the vector is the same vector because you're multiplying the vector times 1. Standard basis vectors. So same as in 2 directions, we're going to have basis vectors on the 3 axes. We're going to have 1 on the x-axis, we're going to call it I. 1 on the y-axis, it's going to call it J. And then 1 on the z-axis, we're going to call it K. These are the standard basis vectors which have a magnitude of 1, and the components of each one. I is 1, 0, 0, since the magnitude of this is 1. on the y direction, j is going to be, now it's going to be 0 on the x-axis and 1 on the y1, and then k is going to be 0 on the x-axis, 0 on the y-axis, and 1 on the z-axis. Here we have a vector, 3 components, ax, ay, and z. This same vector can be noted in a different way using the standard basis vectors. So this same vector with the component ax on the x-axis, the ay on the y-axis, and az on the z-axis can be a equals ax times I plus, because this one is the basis vector on the x direction, plus ay times the vector on the y direction, the basis vector, sorry, j, plus az times k, which is the basis vector on the z direction. Unit vector is a vector whose length is 1, and it's we're going to call it u. A unit vector is going to be a vector, for example, a divided by its magnitude. That's how you that's the definition of unit vector. And we have you're being asked, sometimes you're being asked unit vector with a certain direction. How do you calculate it? U is vector divided by its magnitude. Example 3, find the unit vector in the direction of vector 2i, remember I, x direction, minus j. Since we just have j, we know that this constant here multiplying j is -1, and this one on the z direction is going to be -2. We're going to denote this vector as 2. Remember, 2, the constant on the second variable is going to be -1, and then on a z it's going to be -2. So at the end, u is going to be the vector divided by its magnitude. So square root of each component squared. 2 squared, 4, plus -1 squared is 1, plus -2 squared is going to be 4. This is 4 plus 1 plus 4 is 9. Square root of that is 3, so it's 1/3 out, times the vector on top to the initial vector. And this is u. That's the unit vector. And that's all I have to say about vectors. Yep, I think I covered most of it. Thank you.